Spasibo большое. So I'm looking into this kind of properties, void safety. So this is a diagram from the PhD dissertation of Alexandre Kaktinkov, who is actually here in the room, a dissertation at ETH, and he studied a topic in which a number of us have been quite interested in for quite some time. It's void safety, also known as the absence of null pointer dereferencing, right? So the problem we're talking about is a program that performs something like x.f, sorry, it's not very convenient, and x is null. Okay, boom, the whole thing crashes, the plane goes down, the stock market crashes, and so on. So now, just to point out that this is a real problem, Alexander went into the records of the main security database vulnerabilities and the common vulnerabilities and exposures database, and found that a significant number of crashes are security attacks, some with really serious consequences, are actually connected with a void code, as we call it, a null pointer dereferencing. And if you look at the details, if you go into the CV database, you'll see that it's everywhere. It's in products from Microsoft, from Adobe, it's in JPEG, absolutely everywhere. You have this kind of problem. And if you don't believe me when I say it's important, maybe you'll believe Tony Hoare, who says it's his billion-dollar mistake, which is kind of right. It's also wrong in at least two ways. First, it's probably more than $1 billion, and second, it's not his mistake because don't tell him, right? But he didn't invent the null pointer. I mean, here he says he invented a null pointer and lived ever after to regret it. Well, the second part perhaps, but the first part, as early as 1959, there was a nil in Lisp. So he didn't really invent it, but still. So he says it's $1 billion mistake, but I couldn't resist the temptation to put in a null reference in the language algo-W. This has led to innumerable errors, vulnerabilities, and system crashes, which have probably caused $1 billion of pain and damage in the last 40 years. So this is the kind of problem I'm looking at. Another important application of the work that I'm going to present is alias analysis, which is basically finding out whether a.b.c and x.y.z.q might possibly point to the same object during execution. So this is unlike the previous topic of void safety, on which there is really little literature. Apart from Alexander's thesis and some other work, here there's a huge literature, hundreds, thousands of papers, but the results are not very good. The precision, I'm going to define precision in a few moments, is typically bad. So So that's what I'm going to talk about. So when you give a keynote, you can normally you choose a very general, visionary topic and so on. That's not what I'm doing today. What I'm doing today is that I'm describing some of my own work. So I really appreciate the SECAR conference. It's always nice to be to be invited to give a keynote, but the real test is whether you're invited to give a second keynote at the same conference, because then, the first time you're just trying out, the second time you can probably think that you didn't do too bad of a job the first time. Let's see if there's a third invitation. So Yulia Krychkova invited me to give this keynote, a second one, and I actually recorded the call. So now, of course, I know what's wrong. And of course, yeah. No, it's not working. No. Okay, let me try again. I'm only a computer scientist. I don't need to know how to use the laptop. The speakers. It worked like 5 minutes ago when we tried it. Okay. So this is the recording of the conversation. Oh, except that it's not showing. Never mind. Okay. Oh, I see. So when it's either it's okay. Я тоже. So yeah, this was the invitation. So it was obviously impossible to resist. So it's a technical talk, and it's kind of what I did last summer. It's something. So it's something. I wrote a paper first with the theory, and then I implemented it. So I'm going to show you my program, and which is under development. So this is the kind of thing I'm looking at. Object structure. So you take an object-oriented program in any reasonable object-oriented language, actually in unreasonable object-oriented languages as well. I won't say which ones these are. You stop it. At some point in the program, you stop execution and you look at the object structure, maybe using the debugger, if you have a debugger that enables you to explore the object structure. So it's not going to be as multicolor as this, but it's going to show you a structure like this. Right? Something probably much more complicated, but you have objects, so I've given them names like P1, P2, P3, H1, but these are just for the discussion. And then you have references between those objects. We also have some fields which are things like integers or strings, and these we're going to ignore completely. Okay, we're just going to look at the reference structure, and what I want to do is to analyze properties of this reference structure. So for example, you can see that spouse.spouse, I shouldn't point here, I should point here, spouse.spouse, it goes back to the original object P1 and so on. So that's all. That's all I'm going to talk about, finding properties of these object structures. And it's not just for the sake of drawing nice pictures. So we are going to be able to answer questions such as aliasing. I mentioned this already. So in this particular case, as you can see, spouse.spouse.boss.home is the same as home. It's alias to home. That is to say, well, this is a pretty complicated situation here, actually a pretty dangerous situation in which you work for your husband. I mean, your husband is your boss. This is kind of dangerous, right? But let's not go into this. What's important is that the boss of your spouse the boss of the spouse of your spouse shares a home with you. That's what it's saying. And of course, our object-oriented structure can model very complicated, very advanced situations like this. The clickers here. Another one is, so these correspond to the two major applications that I described at the beginning. Another one is voidness or nullness. Okay, null, void, it's the same thing. So here you can see that boss.boss.home, boss.boss.home is void. There's no, I don't represent null pointers. There's just nothing. So there's no value, there's no object represented by boss.boss.home. It's null or void. So that's the kind of questions that we're going to be able to ask with the tool, the theory and the tool that I have, that I'm going to present. So here's a more complete list: void safety, null pointer detection, the first thing I talked about, the billion-dollar mistake, alias analysis, which I've worked on very much, and there's previous work which implements some of the ideas that I'm going to describe here, but this is new work. Change analysis, which is very important for software verification. It's the automatic analysis of what a routine can change. Okay? what an operation can change. Because in program verification, it's relatively straightforward to say that if you have a deposit operation on a bank account, then it increases the balance by whatever money you have, a number of rubles you have added. You are depositing. Okay, that's easy. What's not so easy to account for in program verification is to say that the owner of the bank account has not changed, the number of the bank account has not changed, the branch of the bank branch of the account has not changed, and so on. So if you list all of these, then your specification becomes completely unmanageable, far too complicated and very brittle. It will have to change very often. Reachability is another of the questions we're going to look at. That is to say, is it possible from one part of the heap, one part of the object diagram to reach another? Separation properties. So reachability plays a big role in an approach which has gained some popularity in software verification. Separation logic, which has in particular an operator written like this. So it's like an AND, but it says that P holds in some part of the heap, some part of the object structure, Q holds in some other part of the object structure, and they are distinct. So it's like an AND plus disjointness. Not just distinct, but you cannot reach one from the other. You cannot reach an object of the place where P holds from an object of where Q holds, and conversely. So we can handle this. Presence of cycles that we can show, absence of cycle with some qualification which I may or may not have the time to give, and in general anything having to do with the object reference structure. So it's very important. Когда кто-нибудь говорит о своем подходе, очень важно узнать не только, что он делает, но тоже настолько важно узнать, что он не делает, что какой подход или система или метод не делает. Это не только вопрос умственной честности, но это просто для понимания. Потому что, чтобы понимать то, что он делает, надо знать предел. Okay. Предел, scope. So here is the scope of this stuff. If you ask me questions about the object structure, I can answer them. But if you ask me questions about, for example, things like the number of objects, I cannot. Maybe I can give you a minimum. I can give you a lower bound, but that's about as much as I can say. Also, anything that has to do with something else than the object structure, I cannot answer. Okay? If you ask me whether n is going to be less or greater than 25 at this particular place in the program structure, there's nothing. I cannot help you with this. I can help you with other tools that we have developed, program provers, which are not yet interfaced with this, but not with this work. So I'm going to show you my working version. So I'm absolutely not ashamed. I'll give you my. I'll show you my program, what's and all in the current state of development. Actually, I changed a few things this morning. It's still under development, so it's fresh off the oven. And I work on the core engine. Okay. So not on interfaces to other languages. So I've defined a core object-oriented language, which is not a real language. It's kind of a concentrate of the mechanisms of major object-oriented languages. And then at some point, we need to interface this with Java. We need to have a Java version, a C# version, a Kotlin version, whatever. That will be for later. So in particular, don't criticize the UI. I mean, criticize the UI, the user interface, as much as you like. That will be fine with me. It's just my user interface. It's for me to test the system. And I was fortunate to have help from one of my colleagues at Eiffel Software, Jocelyn Fiat, who built a small user interface, which is better for demos. But it's really not the interesting part at this point. The interesting part is the core engine which I'm writing. And I guess I have about 6 weeks more work. Of course, I'm a programmer, meaning an optimist, but I think the core engine will be ready by about late November. So before I did this, of course, I worked on the theory. And one thing I would like to point out is that this is very tricky stuff. And at least it's tricky for me. So maybe it says more about me than it says about the domain. But I've made mistakes again and again and again. Fortunately, I have some really smart colleagues who catch my mistakes. But it's very easy to believe your own intuition intuition is wrong. So let me test this. So what do you think of this particular statement about aliasing? Who thinks it's true? Come on. So who thinks it's not true? So why? I'm not asking the absolute experts in the field. I mean, for
the I value. We can change the I value afterwards.
no, it's not like. No. Why could be a side effect producing function? Is that what you mean? No, it's simpler than that. I mean, it's not some kind of bizarre trick. Okay.
It depends on.
Well, if we copy the value, then not.
No. I'm talking about pointers. I'm talking about aliasing. So these are references, pointers. For this discussion, references and pointers are the same thing. Yeah, at the same time. We have type checking where, yeah.
Yeah, I think we're Alias.
Okay. So there was a camera here which recorded all the wrong answers, which we're going to send to all your acquaintances and publish on Facebook and so on. So yeah, the answer is no. And you are going to be really upset at me, even more upset than before. Just assume that y is x dot a. So you had a situation like this, and after the assignment, x is now the old x dot a, and it's certainly not alias to x dot a, okay, which is this. Okay, so it's this kind of thing. I mean, this one is pretty elementary, I should say, but there are much worse cases than that. So here's about framing. Framing means change analysis. So and now you're probably guessing the answer, but what interests me, if you answer no, is the counterexample, right? Is why not? So after the assignment, X receives Y, and here, yeah, we're still talking about references, okay? And X is a variable, Y is an expression. It actually could be, there could be both variables in this case. So this assignment can only change X, and of course, since these things, are references, then of course, if I change X, I also change anything that starts with X. So X dot A, X dot whatever is also going to change, right? That's clear. But this is the kind of expressions that we have. So can anything else change? Going once? Going twice? Okay, well, you're again going to be very upset at me. Let's assume that so here aliasing comes in. Comes into the picture. Let's assume that I have T, which happens to be at that particular point in time, maybe not in all executions, but in some execution, T is a self-reference to the root object, right, to the object on which we are applying this assignment. So this is also going to change T.x and T.x.a and the whole farrago. And it doesn't have to be direct aliasing. If I have U and V, okay, which such that U dot V is alias to this. I mean, one is this, right? It's a root object, this or current, as we call it in iPhone. So it's also going to change U dot V dot X and U dot V dot X dot A and so on. So the field is, this area of study is full of minefields like this. And believe me, along the way I made many mistakes. And in the end, I wrote the paper and I proved every single property, however trivial it looked. I didn't do a mechanical proof. Unfortunately, I didn't have the time or the patience. It's only manual proofs, but I'm pretty confident about my results. Okay, the other point to mention here is that we are dealing with undecidable problems. That is to say, there's this thing called Rice's theorem, which basically says, it's a bit more complicated, but basically it says that any interesting problem in computer science is undecidable. Okay. So, and of course, all these problems fall into that category. So aliasing is undecidable, voidness, null pointers, all this is completely undecidable. And so the proper answer to this is Oh no, so what? Okay, the very definition of a computer scientist, a term which, by the way, which I take to include software engineers, right? The basic definition of a computer scientist is that before he brushes his teeth in the morning, he has already tackled an undecidable problem or not, and that is actually more likely than the average software engineer actually brushing his teeth. So that's what we do for a living. We solve undecidable problems. So what does it mean? It doesn't mean that undecidability is not relevant. What it means is that we have to make a sacrifice between soundness and precision, a trade-off. And the trade-off basically means sacrificing some precision. So let me explain these terms because they're often not very well understood. So consider an analysis, static analysis of a program. So a tool that takes your program, like my tool does, and which tells you things, properties about your program. Okay, we call this an analyzer, and it performs an analysis. So it analyzes for certain properties. And an analysis can be sound or it can be complete, or it can be unsound or incomplete. So here's a very simple example. The property of interest is that this program will not crash, will print something. And there are two versions of the program which both print 1 over A. And in the first version, prog1, A is 1. In the second version, A is 0, which of course is going to be problematic. So what does the analysis answer? If it answers no in both cases, it's sound, right? Sound means if whenever it answers yes, P holds. So it's prudent. Okay? This one is kind of overly prudent, which means, by the way, that it's very easy to write a sound analysis, a sound analyzer for any property. You just answer no all the time, so it takes about 30 seconds to write that analyzer, and it's sound. Okay? It's not very useful, but it's sound. So this is the first case. The second case is we answer yes for the first program and yes for the second one. So it's complete, because whenever the property holds, it answers yes, and your property only holds for prog1, right? So it's complete, but unfortunately it's unsound. So the one we want is the third one, which correctly says that for prog1, yes, everything's fine, and for prog2, no. And there's a fourth variant, which I call unsound incomplete. The technical term is stupid, because this one tells you exactly the reverse of the truth. So if you write analyzers like that, you're not going to be very successful. So this is soundness and completeness. Now, typically we want soundness, because we don't want to say, you're blessed, everything's fine, when it's not true. So in general, you want soundness. This is not an absolute rule, but this is at least the starting point. And so what undecidability tells you is that you cannot guarantee full soundness and full completeness together. That's really what it means. So you are going to have a few false alarms, because we sacrifice completeness. So in practice, it's not completeness that we aim at, because it's impossible together with soundness. What we aim at is a more quantitative notion of completeness. So completeness is binary, right? It's complete or it's not complete. That's not practical. In practice, we want precision, which means let's see how many false alarms, cases in which we say yes, we say no, but in fact it would be okay. Anyone has used lint for C? You're not old enough, right? You're just too. So lint is the mother of all static analyzers for C, and lint is typical of the practice of this game. Anyone who has worked with or worked on static analyzers knows this. The name of the game is precision. Nothing else really matters. What I mean is this: you get a static analyzer like lint or something more modern, and the first time you run your program you run it on your program, you are really happy because it tells you things that are wrong with your program. And then the second time, the third time, you start noticing that there are lots and lots of spurious messages, useless messages, which tell you that things are wrong when in fact they are not. And after 2 or 3 times, people just give up. Okay? People just stop. So if you're not very, very precise, if you have false alarms, then it doesn't work. So this is really the name of the game here. Okay, so now I'm going to show you what the tool does. So let's consider so as before, we stop the program at a particular point, and we look at the object structure. But of course, it's going to be different in different executions. So here's the object structure in the in one execution, and in the second execution, H disappears. In the third execution, at the same place, B, instead of going to this object there, it goes to the bottom right one. Okay? So ideally, that's what we would like to be able to say. But we can't, if only because the set of executions is typically infinite. Okay? So instead, what we're going to do, and this is the core of the method, we're going to compute an over-approximation and an under-approximation. And the over-approximation contains all the objects and references that are there in at least one execution. The under-approximation contains those which are there in all executions. And so we kind of bracket the reality with an under-approximation and an over-approximation. And we'll try to make these approximations as good as possible. So you see that here we have only one execution, so the under and the over are the same. In the second case, the over-approximation still includes H, okay? Because, well, it's not here, but it was in the first one, so we have to accumulate. And on the other hand, H doesn't appear in the under-approximation. And in the last one, we keep everything for the over-approximation, and we keep only the 4 references here for the under approximation. So that's the idea. To a certain extent, this is it, except that this is where the real difficulty begins. So the general idea is, I'm just repeating what I just said as a general principle. If an element exists in any execution, it exists in over, and if it exists in under, it exists in every execution. So that's what we're going to do in this approach that I call duality semantics. Now, what's really interesting is that you need both. Okay? And I'm not really aware of people having done that before. I mean, static analysis has a lot of work that has gone into it, but I haven't really seen this. I mean, the notions themselves are not new, but the idea of computing both, as far as I can tell, is new. So, for some properties, like may alias, is it ever possible that a.b.c will point to the same object at x.y? Well, you need the over approximation. For a variant of aliasing which is must alias, is a.b.c always going to be equal to x.y? It's not what's written on the slide. You need and the under approximation. For attachment, is it always the case that x is not void? You need the under approximation, and so on. Okay? So that's the strength of the approach, is that we're going to compute both. Now, from what I just told you a slide ago, it would seem that we just compute the union and the intersection, and that's it. Okay? Unfortunately, union being over, intersection being under. Unfortunately, the world is not that simple because we have unbounded structures. So for example, this little program, which you will see in a second in the tool, it's finite in the sense that it always creates a list of n elements, but n is variable. So potentially it's infinite. So if we try to compute the over approximation, it's going to be infinite. Okay? So we cannot deal with infinite structure. So what do we do in such a case? We stop. We cut it off. So we choose a certain n, big N, and we over approximate all the missing ones in the over approximation by letting this particular object stand for all the others that would come afterwards. And for the under approximation, we can always ignore stuff, right? So we just stop there. Okay, and so this is what's going to guarantee finiteness. So that's the basic idea. And now I'm going to show you the tool. So I have a little programming language called COOL, Common Core Object-Oriented Language, and it has assignment, it has remote assignment, it has loops, and so on. So let me, so let me actually run it. So these are my standard examples, and these are just the examples that I use for myself to test stuff. So for example, well, here's a little conditional. So the conditional I hope it's, I don't think I can change the font in this user interface. I hope it's readable enough. The conditional is written either something, then bracket, something, and so on. So I ignore at this point, not internally, but at this point, I ignore the conditions. So it's an if then else, but just consider it as being a non-deterministic choice. That is to say, this program is going to execute either C receives A, sorry, or C receives B. So why is this not a loss of generality? It's because, in fact, we have the ability to prefix any instruction by a condition. So by choosing a condition which acts as a guard, then we can have the general if then else. So this is actually much more general than if then else or switch. It's a kind of general mechanism for conditional instruction. So this is the result of the analysis. And it's very simple. You can see it on the left in text form. You can see it on the right in graphical form. It's the same thing, expressed differently. You can see that from the root object, again, the root is this in Java terms, current in IFO. So it's the current object. And so the solid line indicate references that are there in all cases. So they are in the under approximation. Now, initially, I had an implementation that separately computed the under and the over approximation as two different diagrams. And then I thought, look, this is stupid because everything that's in the under approximation is also in the over approximation. So now I have a single diagram, but it actually makes things quite complicated internally. And so the dashed lines correspond to links, to references that are there only in the over approximation. So you can see that A, which is created initially, always exists. Okay, same thing for B, but because we can execute one or the other, then C can be either 2 or 3, can be alias to either A or B. So more or less at random, let me take another. Yeah, this one is not very interesting. Let me take a loop, okay? So here I show on purpose the iteration because there's an iterative algorithm, so it's a not absolutely trivial loop. It's also a little bit artificial. Let me take a more interesting loop maybe. Oh yeah, alternating values, okay? So this one is interesting. You see what it does. I hope you see what it does. It creates A, and then B is assigned the value of A. So B and A are always going to be firm. The references are there. But and then we percolate the values. So each time we get one more. Okay. So I know there's not much time left, but let me show you some of the code and actually play with the code to mention two things. So first, so this is the iterative mechanism for loops. And let me make the font as big as I can. And which still. So what's really interesting, the first thing that's really interesting is that it iterates as long as something changes, okay? So initially, just because I was a bit scary, I'm not a very courageous person, I had put a kind of guard here. When we reach 10,000 iterations, perhaps it's time to stop, okay? But now the theory says it will always stop, okay? So it just iterates as many times as needed until it reaches a fixed point. Fixed point meaning it doesn't change anything. So as you can see, it's commented out. On the other hand, let me add something here, which is that I want to stop after 2 iterations, okay? Okay? Just to see what happens, because showing you, just showing you the result once again. This was alternating value, yeah. You can see that all these things, C, X, D, E, and F, because we have iterated enough, they're all now going to be potentially execute pointing to 2. The loop means execute 0 times or 1 time or 2 times or any number of times. Okay, it's not bounded. So now if I do it at most twice, so let me put back what I had written, then it's interesting because it shows you the fixed point in progress, right? I'm just artificially going to stop it after 2 iterations. And you can see that only C, X, and D have been assigned, so to speak. And the others, E and F, they would require more iterations. So the other thing that we have, let me remove I'm almost done with the demo and that part and the talk. Okay, let me just remove this and maybe recompile to make sure. Actually, I don't really need to. So yeah, one thing that you can do, and the user interface is not very nice here. At least it's, I need a bigger screen. But you can have instructions like probe. So this is really the end result. That's what we want to do in the end. We don't just want to see nice pictures. We want to ask questions such as is this going to be a null pointer? Is this going to be alias to that, and so on. So you have instructions like this in my little programming in the cool language. Then you can say, is a.b.c always non-void, always non-null, attached a.b.c? Is it possibly void? Can a.b.b be an aliased to, can it be ever aliased to b.c or to some other examples? And so we correctly compute all these properties. You can see, for example, that with this particular example, if we take a.b.c and we test whether it's always not void, well, that's not true, because C is an over-approximation reference only. So if I were asking, can a.b.c be not void, the answer would be yes. But here the answer is no. Okay, and we have all these probes, and we can, this is basically all the kinds of properties that I described at the beginning, reachability, the star of separation logic, void, aliasing, alias, must alias, everything is there. Okay, so to a certain extent, this is the end, but it's not quite the end yet. There's a little more. There's 3 more slides coming out after that. So what I've presented is a general approach to analyzing object structures. It's potentially applicable to any language. Let me clarify this by saying that when you start having pointer arithmetic, like in C or C++, I don't quite yet know how to do it. I mean, everyone is scared of pointer arithmetic, except apparently the designers of languages like C++, so I don't know yet. But modulo this reservation, it's applicable to all modern object-oriented languages. But by the way, for Eiffel, we don't need void safety, right? Eiffel is void safe. So this kind of the null pointer dereferencing I mentioned at the beginning, it just cannot happen in Eiffel. It's called statically, and there's something in this direction actually in Kotlin as well. For everyone else, they need this badly. So I described to you very briefly this tool under construction, the object prober. What I didn't emphasize very much, but it's absolutely fundamental, is that the precision is adjustable. Because remember this constant n, meaning that after n execution of a certain creation instruction, I just ignore it. I just keep the object that I had created last. Okay? But n it can be the same for all creation instructions, or I can tune it for every creation instruction. So if I use a bigger n, then the precision is better. And but the computation time is also better, is also longer. Okay? So what I really like in this approach is that it's completely adjustable. So if you want, for example, interactive feedback from your IDE, you're going to choose a small n, and then you get the basic errors right away. If you are ready to release a major version of your tool for a deployment, then of course you run your program for the whole night in order to have a very big n. By the way, it's quite efficient. Okay? The biggest I've tested so far is a program of about 6,000 lines on this rather slow laptop, and it takes 20 minutes, okay? So it seems to scale up. I mean, I've been absolutely obsessed with performance. I'm not saying it's optimal yet, but it's really meant to be a practical tool, right? It's not a research topic, actually. I have written this paper, but I haven't even published it. I'm really interested in the tool, and this is really a commercial project. And by the way, I'm looking for collaborations or financing to turn it into an industrial product. So it's sound precise, in fact. Okay, so let me, yeah, so these are, I benefited from the help of many people. Yeah, let me conclude by mentioning that, you know, part of the reason for giving talks like this is a kind of a psychiatric assessment that I'm asking from you. So I've given you my part, and now I'm expecting your part to help me. Because, you know, this is from the movie A Flew Over the Cuckoo's Nest by this great movie of Milos Forman. And the first 5 minutes are really interesting because you see the insane asylum and all these doctors who are discussing the cases of the inmates, you know, the psyche, I guess, and very seriously. Until after about 5 minutes, you realize that these are actually the inmates, okay? Because the real doctors come in and tell them, okay, enough played, guys, now let's go to the serious stuff. And so to me, this is a metaphor for life in general, because you never quite know whether you are inside the asylum and you are the crazy ones, or whether it's the rest of the world that is crazy. And it's very difficult, you know, like in this old Soviet joke about, you know, dokažite što vu nije verblut. It's more or less the same general idea, right? It's not that easy to prove that the rest of the world is crazy and you are the only sane one. So in the case of psychiatric asylum, as in the case of Eiffel, the empirical evidence is strong. That is to say, there are typically more people outside of the asylum than inside, and there are far more people not using Eiffel than using Eiffel. So, but I think they're the ones who are crazy. So, tell me in a couple of minutes what you think. I mean, yeah, that's the psychiatric examination that I'm getting for free as a consequence of this. So let me show you a little. Let me lift a bit of the veil on the implementation of this. It's not a very big program so far. It's about 10,000 lines, but it's fairly intricate code. It represents things like this. So let me reveal a few of the implementation decisions. A diagram like this, it's actually mathematically, it's a multigraph, is represented by this kind of structure. So for each link, for each reference, like this one, for example, you have a triple. This simply means this is from object 26, a reference labeled T, to object 57. Okay, so that's the triple table. However, it turns out that for the needs of my algorithm, I also need a table, another data structure that gives me, for a given triple, for a given object, what are all the triples that start with that object. Like, for example, so it's an array of lists, right? An array of linked lists, which for object 26 tells me that there's this triple which begins with 26 and that one and that one and that one at the end, okay? And then there's triples with, which is the same thing for a given tag. So it tells me that for T, there's this one and that one and that one and that one. And then there's triples too, as you can guess, and there are many other, well, several other redundant structures, like, for example, the successors of an object for a certain label. So imagine the difficulty of keeping all these different viewpoints consistent. Okay? And so for me, it's really not a problem, or at least the problem itself, in the sense that I have invariance, and I don't really know how to work without this. So yeah, this is the class invariant. It says, I'm sorry, it's at the end. It says things like this. I have actually reproduced a part on the slide because it's easier to read. So for example, this one's here, which is a set of for rows. So the syntax is this: when in mathematics I want to write that for any x in a certain list, a certain property holds. The way I write it in Eiffel is like this, okay, across. And it's the same thing, just expressed in a programming language syntax. So, you know, it says things. So this is like three levels of nesting of quantification, which basically say that whenever I have the triples from list, all the triples begin with the triple with I. If it's triples from of I, of object I, then all the triples that I'm going to find in this list begin with I, and so on. So it expresses all these things that are in the back of your head anyway, but which people do not express. And of course, I made many mistakes along the way, but I almost never had to go into. Yeah, I'm finishing. I made many mistakes along the way. I don't know if I'm more sloppy than others, but I almost never have to do what people usually do, which is to go into the results and suddenly see that a particular result is not what it is, or there's a crash, and then spend the night debugging. Basically, the mistakes come up by one of these properties being violated. And there's one of the options of the interface, which is, if I still have it, yeah, it's this one here, which tests all the examples, okay? So it's going to run all the examples. It's just running the whole test suite. And this is exercising, even though it's not a very big test suite, it's exercising literally millions of these little checks, Because imagine all these three-level quantifiers, nested quantifiers. We are checking every possible detail. So when this test suite completes correctly, which is just did, I actually artificially shortened a few of the examples in order for it to complete right away. I can go to bed and not wake up at 3 a.m. So the question for me, to me this is obvious. I've been doing this for decades, except that the mechanisms are much more powerful than they used to be, because it used to be fairly difficult to write this kind of contract with existential or universal quantification. Now it's trivial thanks to these notations. And so, it's for you to tell me whether I'm crazy or the rest of the world is crazy. I think the rest of the world is crazy, but I accept that the evidence is against me, okay, the empirical evidence. So what remains to be done is, go-to. I want to have a go-to and routines. I know how to do them, but I haven't done it yet. And this, I don't have the time to explain. So the last thing I really wanted to mention in connection with my description of the programming process is that it's very important to program. In the previous or second to previous session, someone cited the saying that cypherpunks should code. I think that was the citation from one of the original cypherpunks. I'm not a cypherpunk, but I'm a software engineer, and I admit that for too many years I didn't code very much. I was teaching software engineering, and I always coded a little bit, examples, things like this. But the experience of writing a difficult and relatively big program is absolutely irreplaceable. So I discovered it again. Big news, it's tough, and it's also somewhat emotionally charged. I think it's a little bit like living a great passion with a very demanding mistress. So she's very volcanic. Okay. So one moment she's happy, gives you congratulations and so on, and the next moment she's absolutely awful. And I'm talking about the compiler here in the environment. Sometimes you hit a problem and you have absolutely, and you're in total despair. And it's also, it makes very difficult for people around you to interact with you. To me, it's something that you really need to concentrate on several hours, possibly several days in a while. But it's really, I wouldn't recommend that anyone teach software engineering without programming himself. And I heard yesterday in one of the panel the comment that programming is only 1/6 of software engineering. That's true. On the other hand, it's also saying that so the criticism, why do we talk so much about programming here at this conference when it's only a small part of software engineering? Yeah, sure. But it's like saying, that in Formula One racing, Cars are only a small part of the whole organization. Drivers are only like 1% of the employees of the Formula One organization. It's about the same thing, right? Yes, programming is a small part, but in the end, that's what it comes down to. And yeah, it's not absolutely clear to me who are the crazy ones. Any questions?
Бертран, спасибо за отличный доклад. Вопрос. У меня 2 микрофона, это я буду кидать, это я буду ходить. Вопросы можно задавать по-русски или по, как вы слышали, Бертран?
По-французски лучше.
3 языка. Можно по-французски, только я не пойму. Вопросы? Так, я вам кину.
Здравствуйте, спасибо большое за доклад, было очень интересно. Вы прямо рассказываете про код, это все, что очень хочется услышать на таких конференциях. Вот, наконец дождался. Не на те просто ходил лекции, а вот на вашу попал правильную. В общем, смысл в том, что вот я разговаривал с людьми, которые свой анализатор, PVS-студию здесь рекламировали в коридорах, они рассказывали про статический анализ, что я вас спросил, а что вот у вас, какие прям вот направления перспективные, вот инновации? Вот вы придумали, что вот сейчас вот у нас программа будет отлично писаться. Он говорит, нет, в основном люди просто опечатываются. Как бы вот большинство проблем — это опечатка. Вот, соответственно, у меня к вам вопрос. Если большинство проблем — это опечатка, то стоит ли сильно инвестировать как бы знания лучших умов человечества, к которым я вас причисляю, к тому, чтобы делать такие интереснейшие вещи, которые вот вы рассказали про under и over estimation, да? Я сразу понял, я в своем инструменте смогу применить это вообще не в статических анализаторах. То есть как бы я хотел спросить, вот ваша деятельность вот именно на этом направлении оправдана или нет? Спасибо. Понятно примерно вопрос, да?
Не совсем. Да. В этом направлении что?
Насколько я понимаю, большинство проблем в том, когда код не работает, в том, что люди опечатались.
Да, нет. Нет, это есть такие, конечно, опечатки, но сами, ну, если взять примеры самых больших и знаменитых ошибок в истории программной инженерии, как Ариан и другие, это не были опечатки, это логические ошибки. Опечатки, конечно, важные, но почти любой метод может их найти. По-моему, интереснее в смысле трудных ошибок — это логические ошибки.
Спасибо.
Спасибо большое, было тяжело.
Спасибо или тяжело? Надо выбрать.
Я хотел вот что спросить. У меня складывается впечатление, я пытался анализировать код с какой-то высокой, с высоты птичьего полета, строил графы взаимодействий. У меня сложилось впечатление, что система имеет свойство дробиться на 3 класса сущностей, и каждый из которых взаимодействует только с одним другим по кругу. Ну, пример того же самого МВЦ, МВВМ. Они, по сути, по кругу взаимодействуют и имеют ограниченные правила по взаимодействию друг с другом. Можно ли построить линтер какой-нибудь, который на высоком уровне способен анализировать связи внутри системы, который способен определить, что появился внезапный класс связей, который не свойственен данной системе, и на базе этого вывести какое-то логическое правило, которое позволит обнаружить, что сущности системы взаимодействуют не по тем правилам, по которым взаимодействует остальная система?
Да.
Спасибо. А как это сделать, на ваш взгляд?
Время надо.
Спасибо.
Еще вопросы? Воспользуюсь своим таким положением привилегированным, задам сам вопрос. У меня бэкграунд в разработке компиляторов, и одна из проблем статического анализа, которая в компиляторах используется, вот Alias анализ, для проведения более агрессивных оптимизаций, то что статический анализ имеет ограничения. Например, если у вас используется откомпилированная библиотека и ставит вызов этой библиотеке, то ничего анализировать вы уже не можете. Это называется black hole в компиляторах, когда все алиасит совсем. Вопрос к вам. Как вы считаете, имею в виду, это статические инструменты верификации именно с практической точки зрения, насколько, вообще ваша точка зрения на статик versus dynamic?
Вы совсем правы. Значит, я сказал, что самая большая практическая проблема — это точность, precision, но это только одна из двух очень важных проблем. А другая проблема — это то, что о чем мы только что рассказали. Значит, то, что мы не контролируем мир. Есть наш мир и есть связи с другими инструментами, с другими вопросами. В таком случае я знаю только одном методе. Это там надо специфицировать. Значит, если если остаться в нашем мире, значит, в моем примере, если остаться в объектированном мире, значит, в нашем языке программирования, как cool, все мы все контролируем. Тогда в этом мире возможный анализ, который совсем автоматический. Здесь для этого типа анализа никакой спецификации не надо. Инструмент просто работает над коде и все анализирует, и никакого участия программиста не надо. Это, конечно, большое преимущество этого подхода, и вообще это большое преимущество статического анализа, потому что не надо, например, написать контракты. Okay? И никто не хочет писать контракты, это я знаю. А если будут интерфейсы с библиотеками, которые не контролируешь, или с другими системами, тогда есть два подхода. Но первый подход просто не практический. Первый подход — это то, что люди называют havoc. Значит, совсем пессимистические гипотезы. Полагаю, что все это как Murphy's Law. Все, что плохо, что может плохо получиться, получится плохо. Но это убивает весь анализ, если это делаешь. А другой подход состоит в том, что если вызов на внешний код, тогда специфицируешь пределы того, что этот код может делать. Конечно, эта спецификация может быть правильно, может быть неправильно, но в этом рамке можно работать. Потому что это как это берет чужой код на тот же уровень, как код, который мы контролируем. Это единственный, это возможный подход. Это можно делать, но требует спецификации.
Спасибо. Друзья, есть ли еще вопросы? Бертранд, спасибо.
Спасибо вам.